Hello everyone. Think about your mobile phone, LED bulb, laptop charger, and solar panel. All of them depend on one important class of materials, semiconductors. In this lesson, we will quickly understand how pure semiconductors are converted into P-type and N-type materials. A semiconductor, such as silicon or germanium, has conductivity between a conductor and an insulator. Pure silicon has 4 valence electrons. Each silicon atom forms covalent bonds with neighboring silicon atoms. But pure silicon does not have enough free charge carriers for most electronic applications. So we add a very small and controlled amount of another element. This process is called doping. The added element is called an impurity. Here, impurity does not mean dirt or unwanted material. It means a carefully selected atom added to change the electrical properties of the semiconductor. There are 2 important types of doped semiconductors. They are P-type material and N-type material. Let us first consider P-type material. P-type material is formed by adding a trivalent impurity to pure silicon or germanium. Trivalent means the impurity atom has 3 valence electrons. Examples are boron, gallium, and indium. Silicon needs 4 electrons to form 4 covalent bonds. But a trivalent impurity has only 3 valence electrons. So one bond remains incomplete. This incomplete bond is called a hole. A hole is the absence of an electron in a covalent bond. In electrical analysis, we treat the hole as a positive charge carrier. When a nearby electron moves into the hole, it fills that hole. But it leaves behind a new hole at its original position. In this way, holes appear to move through the material. So, in P-type material, holes are the majority carriers. Electrons are the minority carriers. The impurity atom accepts an electron. Therefore, trivalent impurities are called acceptor impurities. Now let us consider N-type material. N-type material is formed by adding a pentavalent impurity to pure silicon or germanium. Pentavalent means the impurity atom has 5 valence electrons. Examples are phosphorus, arsenic, and antimony. Silicon requires only 4 electrons for covalent bonding. So 4 electrons of the pentavalent impurity form bonds with neighboring silicon atoms. The 5th electron is left over. This extra electron is loosely bound. It can easily become a free electron and take part in conduction. So, in N-type material, electrons are the majority carriers. Holes are the minority carriers. The impurity atom donates an electron. Therefore, pentavalent impurities are called donor impurities. Let us remember one important point. P-type material is not positively charged as a whole. N-type material is not negatively charged as a whole. Both are electrically neutral. The names P-type and N-type only tell us which charge carrier is dominant. In P-type material, holes dominate. In N-type material, electrons dominate. This concept is the foundation of semiconductor devices. When P-type and N-type materials are joined together, we get a p-n junction. The p-n junction is used in diodes, LEDs, rectifiers, solar cells, and transistors. To summarize, doping means adding a small controlled amount of impurity to pure semiconductor. A trivalent impurity creates P-type material. In P-type material, holes are the majority carriers. A pentavalent impurity creates N-type material. In N-type material, electrons are the majority carriers. This is the basic idea behind controlled conduction in semiconductors. Thank you.